Welcome to COMP501 Foundation of Programming. In this lecture, I will talk about the algorithm efficiency. An algorithm describes the method to solve a computational problem, right? Our algorithm is a step-by-step. Computer programmer and computer scientists should use or write efficient algorithm. In the beginning, we just say write a program to solve the problem. Now you might want to strive for efficient algorithm to solve the problem. Algorithm efficiency is typically measured by the algorithm computational complexity. Now, some algorithms run fast, but the code might be complex, hard to read. Some algorithms run slow, but the code is easy to read. So that is why for education purpose, we show the easier code in the beginning and more complex code later. Computational efficiency or computational complexity is the amount of resource used by the algorithm, and the most common resources are runtime and the memory. And really, the runtime complexity, the runtime is the one that we look at the most. The memory resource is something you don't really have to care much unless you're doing like a low-level design for some embedded system, because the memory is sacred. You don't have a gigabyte of memory. You only have a kilobyte of memory. Algorithm runtime complexity function, like a T sub n, represent the number of constant time operations performed by the algorithm on the input size n. Because the algorithm may vary significantly based on the input data, the common approach identifies the best and the worst case scenario. Like the linear search, which search items from the beginning to the end. If there's a 1,000 item in the list, what would be the best case? What would be the worst case? Same for the binary search. If there's a 1,000 in the list, what would be the best case scenario? And what would be the worst case for the algorithm? Well, for the linear search, the best case is, hey, the item you're looking for is the first item in the list. I find it, I return it, I'm done. The worst case would be the item you're looking for is either last item in the list or not in the list, because I go through the all of the element to do that determination. In the binary search, again, the best case would be 1, and the worst case for 1,000 element would be 10. That's only like a 10 comparison. Algorithm space complexity, SRN, represent the number of fixed size memory used by the algorithm for the input size n. So the space complexity would be the memory usage. The space complexity for algorithm that duplicate a list of number. Remember the array-based list? If I need to increase the size of the array to hold more data, I need to allocate a new list and copy all the data, and the new array has require 2 times more memory. And in this case, so the space would be like 2n plus k. K is just some constant representing the memory used for other things like the counter loop and other stuff that you use in the function or in the program. The space capacity also include the input data and additional memory allocated by the algorithm. The algorithm oscillatory space complexity is the space capacity not included in the input data. So again, that the k is the oscillatory. K is a constant. So your input size can change, but the loop variable, those amount of memory doesn't change. To analyze how runtime of an algorithm scale as the input size increases, we first determine how many operations the operation execute for the specific input size. And this is what the big O notation come in. Big O notation is the runtime of the algorithm, the algorithm runtime analysis often focus on the worst case, because how often you get the best case? Well, maybe 1 in 1,000 or 1 in 1,000,000, but still, the worst case give you the the idea how long it would take to do certain thing as the program at the input side get bigger. The worst case the worst case runtime of an algorithm is the runtime complexity of the input that result in the longest execution time. And other runtime analysis include the best case runtime and the average. So you had the best case, average, and the worst case, but we use the worst case a lot because this really gives you the worst case scenario. So let's do some example. What is a big old running time of the following program fragment? If you look at this here, this one have a nested loop. So this one here have O n square, and this one have a O n. Now, do not tell me this is a n plus n square. Between these two, the n square is the most dominant one. So the answer is O n square. What about this one? This is a O n. This is a O n. Now, don't tell me this is a 2 on. 2 doesn't make any difference. The trend here is still on. Depending on your input, this is a linear. What about this one here? Well, you can see this is a n. So this is a n by n or on squared. In this case, only one algorithm here. So this is a on squared or o n by n. Sometimes people say it this way. What about this one? Is this a on? If you say it's a on, then it's wrong. Why? Look carefully. The I does not go from n to 0 because I get cut in half every time you go through the loop. Every iteration of the loop, I get cut in half. So what would that be then? When you see cut in half meaning divide and conquer. When you see a divide and conquer, this is a O log n. Thank you.